point D is selected on side AB of the triangle ABC, such that the ratio BD to DA is equal to 1 to 3. Now this diagram over here, it does not have the point D, but we're given enough information over here to put point D on the side AB of this triangle ABC. So we know that BD to DA equals what? 1 is to 3. How do we know this? We're given this over here. So let's go ahead and put a point D on the side AB of the triangle ABC. So here you go. I'm not drawing this diagram to scale. This is an approximately drawn diagram that is going to help us visualize the problem. Moving on. Next, select a point E on the side AC of the triangle ABC such that the ratio CE to EA is equal to 1 is to 2. Let's write it down. So we're given that CE to EA, it is equal to 1 is to 2. Let's go ahead and now put a point E on the side AC of this triangle. I'm going to put it over here. And once again, this diagram is not drawn to scale. Next, we're told that BE and CD, they intersect at F. That means we now need to draw a line DC and BE and call this point of intersection of DC and BE as point F. So here you go. This is point F. All right. Next, we are told to find DF over FC plus BF over FE. That means we need to figure out this ratio. Which ratio? DF to FC. And to that, we need to add the ratio BF to FE. How do we do that? This problem. You may think, all I'm asked for is the ratios. And whenever we are asked for ratios in triangle, what do? We look for similar triangles. So you might think, all I need to do is find some similar triangles and find the ratio of DF to FC and BF to FE. You're right, you're on the right track, but not so fast. This problem might look easy at first, but that is deceptive. This problem is actually not so easy. Well, once you figure out the strategy, then it is quite straightforward. But figuring out that strategy, that requires some skill. Now, I have been around several people in the field of mathematics, physics, engineering, pretty much all my life. What I have seen is that some people, they have very good intuition about these kind of problems. They look at the problem and they intuitively know what needs to be done to solve it. While many others, yes, most of the people are in this other category who do not intuitively know how to solve these problems. And that's quite all right, because sure, some people are born with intuition and others who are not inherently intuitive about solving these kinds of problems. Not to worry, intuition can be developed. How? For that, you need exposure, practice, consistency, and persistence. So if you want to develop your intuition to solve problems, what you have to do is keep solving problems. Solve a variety of problems, different kinds of problems, and try to solve as hard problems as you can. You have to challenge yourself. So back to this problem. I came across a problem kind of like this problem a few days ago. And just like I said, when I first looked at it, I thought, boy, this is going to be so easy. But when I started doing it, it wasn't so easy. But once I figured out the strategy, then it wasn't too hard. So what I'm going to do is, when I go through the solution of this problem, I'm going to solve it the way I approached it. Now this problem, I have changed it a little bit. It was asked in one of the math competitions back in 1960s. So yeah, this is not your typical straightforward problem. So buckle up, put the gears of your brain on. I'm about to take you on a wild, wild math ride. So let's look at what's the goal for this problem. We're asked to find what? We're asked to find DF over FC plus BF over FE. That means we basically want to find the ratio DF to FC, and we want to find the ratio BE to FE. Like we said, most of the times when you're asked to find ratios in triangles, you look for similar triangles. Let's see. In this triangle ABC over here, how many triangles are there? And if any of those triangles are similar triangles. Let's make a list of the triangles on this side over here. So first triangle, that is our big triangle over here, ABC. Let's write it down. So first triangle we're going to write down as our original triangle, ABC. Moving on, we have this triangle ADC. I have really bad drawing skills. ACD. Then we have this triangle DCB. Is that all? Not yet. We have more. We have this triangle DFB. And we have EFC. Do you see any more triangles? I do. BCF. EBC. Here we go. EBC. And then we have this DCB. So how many triangles do we have here? 1, 2, 3, 4, 5, 6, 7, and 8. Do we need to use all of these 8 triangles? No. How do we know that? Well, for one, we are interested in the ratio DF to FC and then BF to FE. So we should be considering triangles that somehow has DF, FC, BF, FE, or maybe it will have DC and BE. All right. Now here's a question for you. Are any of these 8 triangles similar to each other? Well, I'll let you see for yourself. Feel free to pause the video here and think for yourself. And let me know what conclusion you come to. My answer is this, that none of these triangles, they're similar to each other. So what we're going to do is, we're going to draw a line starting at E and ending somewhere on BC. So this point over here where the newly drawn line, it intersects DC. Let's call that point as H. And wherever this line intersects BC, call that as point G. All right, now drawing this line, it is a very clever approach to solving this problem. It's going to make it so simple to solve this problem. Well, I shouldn't say so simple because in reality, the solution of this problem is going to have several bits and pieces that we're going to have to put together to compile a neat and clean solution. Now here's the question. Why did we draw this line EG that is parallel to side AB of the triangle ABC? And the reason for that is to get some similar triangles. If I had drawn a line like this instead, could that have worked? You will see that if I had drawn a line, let's say DM, that is parallel to AC, this would not have worked. Why wouldn't it work? I'll let you figure it out after you know why the line EG that we have drawn, that works. Let's see, do we have any new triangles now? We sure do. We have triangle ECH and we have triangle EHF. Hopefully you see them. This triangle ECH, that is this one over here. This triangle EHF, that is this one over here. We also have this triangle HGC. Let's write it down. HCG. We're interested in this line over here and this line over here. Let's now begin with two similar triangles that will have line DC or parts of it. All right, I have copied this diagram over here. Let's consider triangles ACD and triangle ECH. Now these two triangles, these are similar triangles. How do we know that? Well, easy. This angle, angle C, this angle, it is common to both of these triangles. Not just that, this angle CEH is same as the angle CAD. Angle CHE is same as angle CDA. So all the three internal angles of the triangles ACD and ECH are identical. Therefore, these triangles are similar triangles. We know that these are not congruent, that is, they are not identical, because we can see that these are not identical in size. Therefore, these two triangles are not congruent. However, since all the three internal angles of these two triangles are identical, therefore these two triangles, they are similar to each other. So let's go ahead and remove that and instead put the symbol for similarity. So these are similar triangles. Since these are similar triangles, now we are going to set up some ratios and hope that some of those ratios would help us get our answer. Alrighty. So I would say the ratio of CE to CH. These two sides, these are part of the triangle ECH. This ratio is identical to CA over CD, which is part of the big triangle ACD. Let's write it down. CE divided by CH equals CA divided by CD. This might be useful. Why? Because I know the ratio of CE to CA. We're given that over here. And additionally, we are also given the ratio of BD to DA. So coming back here, triangle ACD, it has the side AD. We know the ratio of BD to AD. So let's go ahead and use this AD in one of the ratios. Let's say CE divided by EH. This is equal to CA divided by AD. So all I'm saying is that CE is to CA as EH is to AD. All right. Let's now manipulate these ratios. For this first one over here, write this as CE divided by CA equals CH divided by CD. So basically what we have over here in the original equation is take triangle 1, it's one side, triangle 1's other side. And over here what we have is triangle 2's side 1 and the same triangle's other side. Well, let me write it down here actually. So here's what we have. Triangle 1's side 1, triangle 1's side 2 equals triangle 2's side 1 to triangle 2's side 2. And let me remind you, these two triangles, T1 and T2, they are similar triangles. In this equation, I have triangle 1 on one side, triangle 2 on the other side. From this, what I want to do is triangle 1's side 1 to triangle 2's side 1, triangle 1 side 2 to triangle 2 side 2. I now want to go from this equation to equation that has triangle 1's first side to triangle 2's first side equals triangle 1's second side to triangle 2's second side. And when you do so, you will get this. Of course, we could have performed some algebra over here and gone from here to over here. But once you understand the concept like this, it is far easier than using any algebra. And likewise, I'm going to put this equation over here in the same format where I have CE divided by CA. CE, this is part of the small triangle over here, while CA, it is part of the similar larger triangle, as you can see. And this will be equal to what? It will be equal to EH, which is part of the small triangle, divided by AD, which is part of the larger triangle. Okay, let's go ahead and clean up our slate and move this work up over here. All right. So what we want is this ratio CE to CA. Do we know that? Not exactly, but can we figure it out? Sure can. How? We're given the ratio of CE to EA. This is equal to 1:2. Now this CA over here, what is this? CA is sum of CE and EA. All right. And from up over here, 2 times CE is equal to what? EA. So let's go ahead and put CE, and in place of this EA, let's put that equal to 2CE. And that gives us CA is equal to 3CE. With this information, we can transform the CE over CA to a simple numerical ratio. So CE over CA, let's write that as equal to CE divided by CA. And we know that CA is equal to 3 times CE. So CA is equal to 3CE. This is equal to CH divided by CD. Sure, CE cancels CE and we are left with 1/3. And this 1/3 is equal to CH divided by CD. What does this give us? This gives us CD is equal to 3 times CH. Let's box it in. This might be useful for us later on. Now we're going to apply the same logic over here that we applied to derive CD equal to 3CH. So CE over CA, we know that this is equal to what? It is equal to 1/3. We just showed it. This is now equal to EH divided by AD. And this gives us AD is equal to 3EH. So what we have shown is this CD, that is this entire length over here. This is equal to 3 times CH, which is this. And not just that, this AD over here, this is equal to 3 times EH. So what we're saying is this. This is equal to 3 times this length. Okay. And not just that, this 80, this is equal to 3 times of this EH. Okay. All right, let's leave this here and we're going to come back to it. What else can we do with this information? What else are we given? We are given that BD over DA is equal to 1/3. Let's write that down. In the problem, we're given that BD over DA, that is equal to 1 divided by 3. And from here, what can we get? We can get that DA is equal to 3BD. Now, DA, it is same as saying it is 80. So we're saying that 80 is equal to 3BD. But we just also said that 80 is equal to 3EH. So what we're saying is that 80 is equal to 3EH and 80 is also equal to 3BD. What does that tell us about EH and BD? This tells us that EH is equal to BD. Let's write that down. BD equals EH. Here's BD. And here's EH. These two are same. Okay. This is interesting. Now BD and EH. These are parts of the triangles DFB and EFH. What else can we tell about these two triangles? Let's see. Let's make it larger. We know that these two angles, they are going to be identical. Not just that. This angle over here, this is going to be equal to this angle over here. Why? Because the line EG, it is parallel to line AB. I hope it is ringing some bells. Notice, the line BE, it is intersecting two parallel lines, AB and EG. Do you remember what this line BE is called? It is called the transversal. And these two angles, let's call them as 1 and 2. These two angles, 1 and 2, these are alternate interior angles, and they're going to be equal to each other. So here you go. In the triangles DFB and EFH, not only are the sides DB and EH equal to each other, but there are these three sets of angles that are also equal to each other. I hope you can see that. These angles that are drawn in white, these are vertical angles of two intersecting lines. Which two intersecting lines? DH and BE. And then these angles that are drawn in yellow, they're also equal to each other. Why? Because they're alternate interior angles. And likewise, these angles that are drawn in green, they are also alternate interior angles. So we know that the triangle DFB and EFG, they are similar to each other, but not so fast. We also know that the side DB is equal to side EG. Therefore, these two small triangles, DFB and EFG, they're not only similar to each other, but they're also congruent to each other. Let's write it down. So we're saying that the triangle, which triangle? DFB, it is congruent to triangle GFE. Why am I writing these letters in this order? That is because D is to G, as is B to E. Therefore, D for first triangle is to G for the second triangle. F is common to both. And then B is to triangle DFB, as is E to the triangle DFE. And this is the symbol of congruency, which also means identical in shape and size. Similar triangles are identical in shape, but not in size. While congruent triangles, they are equal in size and shape. So all congruent triangles, they're also similar triangles. But similar triangles may or may not be congruent. I hope that makes sense. Well, think about it. Let's see if we can somehow now make use of this information. Which one? That these two triangles, these two small triangles, DFB and GFE, they are equal to each other. Let's see. What are we asked to solve for? What are we asked to do? We're asked to find the ratio of DF to FC, and to that add ratio of BF to FE. Now we just said that these two triangles, DBF and EFG, they are congruent. That means BF is same as FE. Because the triangle DFB is congruent to triangle GFE, that means BF is congruent to FE. In other words, BF is equal to FE. Let's write it down. Why? Because of this. These three dots, when drawn like this, it means because. Again, this B/C, it is because. All right, so now we know that BF is same as FE. So now that we know that BF is equal to FE, that means the ratio BF to FE is equal to 1. So this part is solved, but this part is not solved yet. So let's now figure out what is the ratio of DF to FC. All right, so let's go ahead and write it down first. DF over FC. Here's what we're going to do. We're going to leave DF as is, and we are going to try to express FC in terms of DF, so that the DF in the numerator, it can cancel out the DF in the denominator, and we will be left with the numerical value for the ratio DF to FC. So here's our FC in the diagram. This FC, can we write this as CD minus DF? Sure can. Let's go ahead and do that. So in place of CF, let's write CD minus DF. Next thing we're going to do is express the CD in terms of DF. How do we do that? Watch this. So we're saying that CD, let's write CD, which is this entire length, as sum of DF plus FH plus HC. So here we go, DF plus FH plus HC. Okay. Now we also know that this CD, it is equal to 3CH. Let's write 3CH in place of CD. Here we go, 3CH. What is this equal to? This is equal to DF plus FH plus, in place of this HC, let's write it as equal to CH. Because all we are writing here are the magnitudes of these lengths. So it doesn't matter if I write it as CH or HC. It means the same thing. And that makes the left-hand side of this equation equal to 2CH. And on the right-hand side, we'll have DF plus FH. Okay, so now we have 2CH is equal to DF plus FH. Let's now return to these two small triangles. Which triangles? DFB and HFE. These two triangles, they're congruent to each other. Let's write that down. Triangle DFB, it is congruent to the triangle GFE. And in these two triangles, the side DF, it is equal to FH. DF is equal to FH. And substitute this FH as equal to DF in this equation over here. Let's go ahead and do that. So here we go, DF plus, in place of this FH, let's write DF. So here we go, DF plus DF equals 2DF. So we have gotten 2CH to be equal to 2DF. Go ahead and divide both sides of this equation by 2. And what would that give you? That would give you CH is equal to DF. Let's write that down. And this is important, so let's box it in. Let's now return to this initial equation where CD is equal to DF plus FH plus HC. We have just shown that CH is equal to DF. And we have already shown that FH is equal to DF as well. So CD is equal to DF plus DF. Why? Because this FH is equal to DF plus DF. Why? Because this HC, which is equal to CH, is also equal to DF. So let's go ahead and write this down. CD is equal to DF plus DF plus DF. That is 3DF. And this is important, so let's box it in. All right, and now we're going to return to this original ratio over here that we are trying to evaluate. So what do we get? We get DF divided by, so in place of CD, write 3DF minus DF. What does this give us? This gives us DF divided by 3DF minus DF is equal to 2DF. I know what you want to do now. Cancel out this DF in the numerator with the DF in the denominator. What does that leave us with? That leaves us with a numerical value 1/2 for this ratio DF over FC. So here we go. We have found that DF over FC is equal to 1/2. So this DF over FC is equal to 1/2. And this BE over FE, we have already shown that this is equal to 1. What we are saying is this: DF over FC plus BF over FE. This is equal to 1/2 for the first ratio, DF over FC, plus 1 for the second ratio, which is BF over FE. This is equal to 3/2. Here's our answer. So like you saw, this problem was not your straightforward problem, even though it might have looked like in the beginning that it was going to be easy. And actually, once we figured out the strategy, it wasn't too hard. Sure, there were several different pieces that needed to be put together to solve this problem, and that's what makes it hard. Other than the fact that we had to figure out that we needed to draw the line EG that is parallel to the line AB of the original triangle. Once you have figured that out, the problem, it is not super hard. And besides, as you solve more and more difficult problems of different varieties, your intuition is going to develop and build up. So if you haven't subscribed to this channel yet, you might want to do that. Why? Because on this channel over here, we're going to be solving several such problems. This is just the beginning. We're going to be solving problems of not just mathematics, but also physics, and hopefully someday also chemistry, because I happen to just love chemistry. All right, so this is it for now. I'll see you again next time. Until then, happy problem solving.